Yeah, right. How are you today? You're already calling the phone. Sorry, you're taller than me. Yes. It's a number. It's not almost. Almost. Won't be long. No, won't be long. Can you imagine the time? It's not outside today. So Megan's in here. And this is Isabella. She's hanging with you. Ryan, you're me, right? So you're gonna be in here. Maybe you want to pretend you come in too. Into the living room. And we got two more that are in your class that are coming. So pick a seat anywhere you're comfy. Maiden's gonna pick a seat anywhere that's comfy for her. You can hang out in here with Isabella. This is Maddox. There's gonna be a lot of sibling shifting with Spanish this year, so that's just how we'll do it. Yeah. Yeah. Yep, that's it. No, actually, I did it wrong. It's Rico, 1, 2, 3, 4. So capital RICO, capital RICO, 1, 2, 3, 4. See, I knew something was repeated. That's why I have it written down over here. This one? Yeah, just 1, 2, 3, 4. So Rico, with the name capitalized both times with the first letter, and then 1, 2, 3, 4. Yep. There you go. Excellent. How was your summer, Orion? Yeah. You got some quail now at your house to hang out. Do you help with them? No, that's all on her, huh? You have what? One left? Yep. One got away. Who's left, Isabella? Which quail is left? Okay. No, the snake one? Yeah, just on Sunday actually. I found it was who did they get? You know. Oh, well, that was one you had a problem with, so you know this was the other man. Oh, the third man that we all thought, man, that young was hard apparently. Yes, we were all like, hey, you know what we got? No. That is wild. Yeah, this is absolutely crazy. Yeah, so it's very first one was like awful stuff. Very built. And I'll show you. His mom sent me a picture of his enclosure. I know. He wasn't in it though. Oh. I also I found very little one about it. I realized it couldn't switch your back now. Yeah. I had a rat in the storeroom at my college that did that. We went in and took that like very like at it. And they have been so he kept all the fairy eggs and then he brought me, yeah, the little, they're like these little tiny eggs that sometimes they make it usually like the first egg just went to it, and it's not a real egg, it's like a little, chocolate egg. But, that helps to say that. But, yeah, so he took the fairy eggs and then he brought me an entire mason jar full of eggs when he came to grill the show, like a full mason jar. So that was pretty wild. I ate them all already, so. He said, why you not sure with his, so yeah. Did you get in touch with Yusuf about the brooder or the incubator? Oh, is he? All right, okay. Up here, I do the people here. Good morning. No, she's not for lab, so it's just a thing for lab. It's crap. It's my understanding. You're gonna eat? User? Yeah, it's not. Oh, it's not. There's a test on this. We don't pronounce it. Yes. So how do you say your number? Yassine. Okay. How do you say your last name? Okay, I'm Sandy. It's nice to meet you. How are you? Right. Come on in, and we'll get ourselves situated. We'll see you later. Well, no lab. So, noon. Yeah, because I have class and then lab. They'll be done at noon. So we'll see you then. All right, thanks. Come on in, y'all. Have a seat.
What do you have? Is it a cat?
I have a dog, but he's in his crate right now.
Oh man, I'm really scared of dogs.
Well, he stays in his crate all through class, so you won't even see him probably almost ever. So he lives in his little, he's in that box right there. See, he's little enough to fit in that box. See the box with the blanket on it? He's in that. He's tiny. Yeah, he's about this big.
Is he how small is he?
He weighs about 13 pounds, so he's not very big. He's a dachshund. Do you know what a dachshund is?
No.
Like he looks just like this, just a little bigger. Same color, everything, just a little bigger.
My brother has a dog exactly like that in field vacation, so he calls it Doggykins.
Okay, there you go. Well, I'm Miss Danny, so I'm your science teacher. We're gonna have fun. It's gonna be a good year. So if y'all, we're gonna take a minute and we're gonna introduce ourselves first. And so tell all your friends your name.
My name is
Okay, this is Yusra. And you're how old?
8.
8. Excellent. And you are?
4.
And how old are you now? 13. Maven's 11. And?
Maybe Yassine and I'm 12.
Yassine is 12. There you go. So for show of hands, who's this first co-op? Is this your first co-op? Your first class with other kids?
Yeah.
Yeah, you've done class with other kids before? What have you done?
Well, just like in general, there's just like.
Okay, with other kids? You do stuff with other kids too? Okay, all right. So very good. All right, so you guys got a checklist before class and it had some assignments on them. And if you started it, you probably noticed that some of them were kind of weird. Like you go in and it asks you, is everything okay in your online gradebook in Teacher Ease? Let's just make sure I don't have any mistakes. Then there was one where you had to download a picture and like change the picture and then upload it again. And that's just so I know that you can. Yeah, what?
I was in an online.
Oh, were you? Okay, all right. So you've done online stuff before. So that's just to check that I know that you can get in there, find an assignment, download something, manipulate it, upload it again, hopefully as a PDF. That's the goal. It's the kind of file we use. And then there was also a lab assignment that went over lab safety, right? And then an assignment that's like how to science. And the whole purpose of that is because everybody, so y'all just said you're like 11, you're 13. How old did you say you were? 12. So 8, 11, 12, whatever, all different ages. So everybody has a different amount of background knowledge before they get here. So we want to kind of put everybody on the same level.
So I've been secretly coloring Rico in my book.
Oh, okay, good. That's good. You're getting ahead of the game. I love it. So yeah, if you saw Rico in the little rat picture at the end of every assignment, if you want to color him, there's that chest right there has some with the lemons. Has some folders on top and you can always put your coloring job in there. And I put them all, you put your name on the front and you color the back.
and I put them all face down so I can't see whose name, and I picked my favorite one, and then you just get a piece of candy when you come in next week. That's all it is. It's just for fun. I put something on it.
We'll have like coloring. I think my room is already filled with it.
Okay. Well, I don't think any of you guys made our grill and chill, did you know? So that was our orientation. It was a couple weeks ago on a Sunday night. We had an opportunity for everybody to come in, and I was going over a bunch of stuff about class. But I think it was your birthday. You had somewhere to be. It was fun, right? So we had stuff to do. So in here, this is only temporary. I usually have a different jar, and I broke it, so I had to replace it. So I have a little bucket. But this is, what's it sound like? Yeah, it is. It's pennies, right? So right here in this box, I have a little tray. It's actually an ice cube tray. But you see, I got your name on every one of those. So the way this works is I'll ask a question, and if you answer the question, even if you don't get it right, if you try, if you participate, then I will drop the coin in the little bin with your name on it. And then on the way out the door, we have a machine full of Skittles. And you can get, it usually gives you 1 or 2 Skittles per penny. You like them?
Those are not stars. They're not those like cube ones.
No, they're just
They're-
Skittles.
Oh, yeah, these are hello.
Oh, okay.
Yeah, those
Starburst? You're thinking about Starburst. Yeah.
are not hello. I never.
Those are too, oh yeah, they're too big. I can't get them in there anyway. Oh yeah, they have gelatin and stuff in them. Okay, that's good to know. So do you guys always eat halal?
Yeah.
Okay, good. All right, that helps when I'm planning stuff for the future. All right. Okay. Are we ready to start?
Yeah.
So some of this you will have seen before because it's a little bit of a review of your How to Science lessons. So if you did that, you'll have seen it before. And some of it's going to be going over what you should have read in your book before you come to class. So you're supposed to read in your book before you come to class and work through your binder. So if you have your binder with you, you can pull it out now. If you filled in any of the blanks, most of those are going to be exactly what I'm talking about. So you can look at what your answers were there and get answers up here. All right. Give you a second to get those out.
I think I moved the chair.
It's all right. Don't worry about it. It moves a lot.
Why does my backpack have to be heavy?
Yeah, because your
Oh,
binder
it
is.
has 2 things.
That's because you got a lot of stuff in there, you know?
Actually, I only have 2.
Oh, well, they're heavy stuffs, I guess. You probably don't usually need to bring your textbook. You can if you want, but you don't usually need to bring your textbook. You definitely, there you go. You did good. You definitely need to bring your binder because you're going to have your lab in your binder. And then also we'll go over like what you've written and studied. So if you open up.
Actually going real lab.
Yeah, this is the lab right here. We use the kitchen as lab and it works really well. We actually have pretty much nearly all the equipment you're ever going to find in a real lab, like a real science lab in like a college or whatever. We have almost all of it. It's not here right now, but
yeah, but I don't know where any of this
it's all stored. You don't need to worry about it. I bring out what we need. The only thing we don't have is like vent hoods, but we go outside if we're going to do something with a lot of fumes, and that only happens in chemistry anyway. So you want to find lesson 1, which should be behind your orange papers. So if you see those orange papers and you move past them, that should kind of help you find it. There you go. After you go past that last orange paper where you get to the green papers. So you want to go to the first green paper. It'll be right here. There you go. So here's where we are. We're at lesson 1. We're going to turn to the first page and look, you've already filled that out. That is perfect. That's what we want. So everybody found it?
Yeah.
All right, so let's go. This is how it works. So what is science? That's the first thing we're talking about. Oh, she knows already. Do you have an answer? That's a good start. Yeah, that's a very good start. All right, so let's get a more specific answer. So science is a system of knowledge, meaning it's what you know, as well as a method to find knowledge. So it is what you know and how you do. It is both knowing and doing. Science is 2 different things, knowing and doing. So it begins with something and ends with something. Does anybody have a guess what it might begin with? One of many options. Yeah.
Science often begins with curiosity.
Curiosity is right. And what's it end with? Anybody know? Do you know?
With more.
You want to guess?
I was going to say observation.
Oh yeah, we're almost there. So it ends with discovery. I'm curious about something. I'm gonna try some stuff to see what I can discover. That's how science works. So what's the use of knowledge? Do you know what the use of knowledge And it's not just knowledge, but it's actually like how you use what you know. So in this case, what we're talking about is technology. So when you think about technology, what do you think of? Like, what's an example? Wires, what else?
Electricity.
Electricity, what else? Computers, yep.
These are
Yeah, but you know what else is technology? The pencil in your hand. The shoelaces on your shoes. These are all technology. This is us taking our knowledge and going, how do we practically solve the problem of keeping our shoes on? Well, I know that if I can make the top of the shoe tighter, it's going to stay on my foot. So what do? I can tie it. There you go. So that is technology too. All of that is technology. Science and technology are interdependent. That means that one relies on the other. They work together. And advances in one lead to advances in another. For example, sometimes we have accidental inventions. So there was a lady named Stephanie Kowalik who worked for a company called DuPont. DuPont makes all kinds of chemical things. Yeah, you know that?
She has a koala called Princess.
Does? Oh, I don't know. Maybe. So Stephanie Kowalik is her name, and she worked for DuPont. And what were you going to say?
Fireworks were an accidental invention.
Fireworks were an accidental invention, yeah. So, but Stephanie was.
Koalas in the forest that brings them, it then takes care of them.
That's a different person. Because this lady I'm talking about is a chemist who worked in a lab. It sounds like koala, but it's koala. Anyway, she was tasked with making a polymer, which is a long chain of molecules, like nylon or something like that. She was trying to make a really strong polymer. And she ended up making something that wasn't quite what she wanted it to be. And she showed it around, and everybody was like, you don't want that. And, that's not what we're aiming for. Try again. But she looked at it. She's like, I think this could be useful. Do you know what that polymer is called now? It's called Kevlar. Do you know where you find Kevlar?
Nope.
In bulletproof vests. Yeah. So an accident has now saved many, many lives, right? All right. So let's look at different kinds of science. So we have formal sciences, and these are mathematics, logic, and statistics. Then we have natural sciences, which is what we do here. And then there's another kind of science up there that involves things like anthropology, economics, geography, political science, psychology, and sociology. Do you know what kind of sciences those are? Those are called social sciences. You know what social means? Like interacting with other people. These are all have to do with behaviors, the way people interact, the way our systems, like economics is how our money works, how we set up our money, that kind of a thing. So we get to natural sciences. They're divided into two big categories. So life science has many categories under it. Life science would be biology in general. So zoology, mycology, microbiology. Yeah, and then we get physical science. So the first one says study of nature properties, matter, and energy. Anybody know it?
There's this fun.
Yep, there's astronomy. Anybody know what the first one is? The first one is physics, right? The second one is what? Study of celestial objects. That means things in space. What's that one? You said it. Astronomy. Yep. Astrology is like zodiacs. Like, are you up? Pisces or Aquarius? Yeah, astronomy. Astronomy. All right, and the study and identification of substances of which matter is composed. Chemistry, very good. And what do you think that last one is? Physical constitution of the earth and its atmosphere.
Geology.
Well, it's actually going to be earth science in general. So it's all of our, so it's what we're doing this year.
Biology is.
Yeah, biology would be a life science though. So it would be, because it's the study of life on Earth. So when we look at earth science, what we do this year is we're going to study what the earth is made of, its atmosphere, its processes, and we're going to touch in astronomy a little bit. We're going to talk about space as well.
I already know that the atmosphere of it is the sun.
So this is something to try and remember whenever you see this little guy spin up. It says engrave it for eternity. That is a clue that this is going to be on an exam. Yeah, that's Rico. And that's a clue. This is going to be on an exam. It's going to be on an exam like, I don't know, your midterms or your finals or big exams, the big tests. So those are things to remember for sure. All right, so we have big ideas in physical science. What do you think this first image is here? The helmet and we're looking for two words. What words do you think? Astronomy. Maybe? Where do you think he's going, guys?
Space.
Space. And what's an hourglass track?
Space.
Time.
Space.
So space and time.
Space.
Okay, so earth science talks and physical science in general is going to talk about space and time. What are those pictures of? Badges for what? Yeah, so that's going to be forces. And then the arrow shows you motion. Forces and motions. This is all physical science, right? And then what do you think that top one is? You know?
The color one.
No, the gray one at the top. What's that, you think? So that one's kind of tricky. It's matter and change. Okay, you see that little triangle? It's not a triangle. It's actually a Greek letter delta. Looks kind of like a D, doesn't it? Right? You ever seen a delta plane? What's their logo look like?
That looks
Triangle,
like a
right?
plane wing.
Okay, delta in science means change.
Called delta.
Mm-hmm. So delta in science means change. So whenever you see delta, or I might say to you, what's the delta in your data? And I'm asking you, what's the change? Energy is that last one. Yeah, so it's energy. Very good.
Should be light.
Yeah, yeah, it could be. So now, this is interesting. Your goal here is to look, each of these is a different color, the words are, right? So you got like pink, kind of a white, a gray, a blue-gray, a lighter gray, purple. See that? Now, you're going to see those words turn up in other places, and it shows you the interdependence, how they're related. So space we're going to define as a continuous area or expanse, which is free, available, or unoccupied. And dimensions of height, depth, and width, all which matter exists. What's matter? What is matter? Matter is just, it's just stuff. It's just anything. Everything is made of matter. It's just stuff. There's matter right here that you can't see because it's very small molecules of gases that make up our air. You're made of matter. Everything's made of matter, right? Okay, so it's matter. All right, and then how would you define time? So time is measured or measurable period of duration or during which an action, process, or condition exists or continues. Time is hard to define, isn't it? Without saying time. It's hard to define time without saying word. So a non-spatial continuum, which is measured in terms of events which succeed one from another, past through present to future. Time is hard to define. But look right here. Do you see how the word matter showed up here? This is matter. So space depends on matter. All right, so this next one, don't tap your foot too loud. My mom actually lives down there and she can hear all of it and it's weird. So push or pull on an object is a force. So an object is made of matter, resulting from the object's interaction with another object. In order for me to push on my desk, my hand has to interact with my desk, right? So it has to interact with another object. Influence that can change. Oh, there's change. Here's change. The motion, here's motion, or velocity of an object, which is matter. Velocity is motion with direction. It's just describing the motion. It's the motion going to the left, to the right, to the up, to the down, right? So how about motion? It's a change with time of the position or orientation of a body, which is matter. So motion of, if I say my bucket went from here to here, it changed over a period of time. It took me about a second and I moved it, but now it's in a different location, right? So motion is change over time, right? And it's also a phenomenon in which an object or matter changes its position with respect to space and time. It was in a different space, right? And that took time. So how do we define matter? It's a material substance that constitutes the observable universe. Together with energy forms the basis of all objective phenomena. What is objective phenomena? Anybody know what that means? Those are big words. So objective means it's something you observe. So observe is using your senses and you can see it and there's no influence of your opinion on it. Subjective means your opinion's involved. So if somebody puts scrambled eggs down in front of you for breakfast and you say, those are scrambled eggs, that is objective. But if you say scrambled eggs are good, that is subjective because it depends on what you think. It's your opinion, right? All right. And then phenomena is just something, some action that's observable. A smell, An explosion could be, it's the plural of phenomenon. If you've heard the word phenomenon, phenomenon is plural. Could be, yep. So how would you define change? A transition from one accepted theory to another or from one employed method to another. So something is different.
Change your clothes.
You can. A process in which one or more substances are altered into one or more different substances. So if you were to do a chemical reaction, you would start with certain substances and have different substances at the end. Anybody ever mixed baking soda with vinegar before? You ever done it? What happens? It bubbles. So that tells you something's being created. What do you think's being created? What new substance? It's a gas, right? You're making bubbles, so a gas is being created that wasn't there before because it's a chemical reaction. So because it's a chemical reaction, we'll be like, oh, what do you know? It's a change. So an alteration, transformation, modification, or substitution. Just things you can do to make change. Energy, we're going to define as the capacity to do work. That is the definition of energy, the capacity to do work. If you have no energy, do you have the ability to work to clean your room? If you got no energy, man, you can't do it, right? No energy. If you have no source of energy, like no gasoline or electricity, is your car going to run? You have to have energy to do work, right? What's up?
How many coins do I have in there?
I don't know. We'll count them at the end. We try to keep rolling during class. So that's why, like, we raise our hands to talk. And I know it's weird because you're probably not used to that. And then we throw in the coins and you get them at the end. So that way we can get through the whole lesson without, like, stopping too many times and getting off track. Sometimes we get off track and it's usually fun and worthwhile. It's also energy is a property of a system that diminishes. That means it gets smaller or less when the system does work to any other system. So here's a good example. Let's talk about if you put gasoline in your car, right? It's a source of energy. So now your car has the capacity to drive. What happens as you drive the car to the amount of gas in your gas tank? What happens? It's going to diminish. Yes, it's going to drain your tank. And then when you get to the point where you've run out of it, do you have any more energy source? Nope. Can you do work? Nope. Very good. Yes, ma'am. No, we have lab. So we'll go from here to lab, which feels different, and then you'll be done. So there's a little, sometimes we have little gaps and we'll do little like activities in between, but we keep moving. Don't worry, we keep moving. We do all right. So it's also any source of usable power, like fossil fuels, that's gasoline, right? Electricity or solar radiation. You can write at any point. If you see something important, you can write it down. If I say something that you want to remember, otherwise you can just read what you've already written, whatever works for you. So our big ideas in earth science are going to be systems. Earth is a system of systems within other systems. So a good example would be, we have what's called the hydrosphere. It's all the water on Earth. So in the sky, in the lakes, in the oceans, in the streams, in the rivers, in the ground, in the rain, that's the hydrosphere, right? That's a system on Earth, but Earth is also within a system. What system are we part of? What's Earth a part of? A bigger system. Think outside of Earth. How about
space?
Space. Well, how about the solar system, right? And then our solar system is part of our universe. Yeah, part of our galaxy, actually. And then the galaxy is part of the universe. So it's systems within systems. It's like, you ever seen those Russian dolls? Where you take the one little doll, there's a smaller doll.
Electricity connects.
Yep. Smaller doll, smaller doll, smaller doll. Okay, so energy, the flow of energy drives the cycling of matter. Yes, so as we have energy flowing through a system, it will drive the matter being cycled. So there has to be, if you have a puddle of water on the ground, energy from the sun will evaporate that water. It will go up. So now it is no longer water. It is water vapor. Our matter is cycling from one form to another. And then it will condense up in the cloud. And then when it gets enough gravitational potential energy, because it has too much mass up there, it's too heavy. All the water has come together into big droplets. Now they're too heavy to be held in the sky, too much mass, then they'll fall, right? So our matter has cycled. Life and the environment. So life, including human life, influences and is influenced by the environment. We're influenced by our environment, aren't we? Does anybody want to go outside when it's 109 and play? I don't. You do? I don't. No way. Question? Question? Do you have a question?
I
Oh, I don't. No. So the unchanging drives change. So physical and chemical principles are unchanging and both drive both gradual and rapid changes in the earth. Our chemical processes, our physical processes don't change. Gravity doesn't change. If I drop this coin, it is going to hit the floor every time. And if I do it enough times standing right here, sooner or later, it's going to ding up my floor, even though it's a little penny. If I do it enough times, sooner or later, that's what's going to happen. So the unchanging, the fact that this is gravity, drives change. It could mess up my floor.
So what does this do?
We'll talk about it later. We're going to stay on topic for now. So after I'm done talking, remind me that you have that question and I will tell you. Cool? No. So modeling and mapping to understand deep time and the scale of space, models and maps are necessary. Can you see the whole solar system with your eyes? No. But if I made a
telescope,
even then you could only see one or two things at a time. You still couldn't see the whole thing at once. You need to draw it out or make a model. Same thing. Can you see the whole earth with your eyes? No, you're going to have to use a globe or a map. So models make things easier to understand. All right, so science is a process and a body of knowledge. Like I said, it's what you know and what you do, right? Be skeptical. What does skeptical mean?
you sketch what you know.
Close, kind of.
Means like, oh my gosh, it's hard to understand.
It is hard.
But when you're like,
Hang on, she's trying. Let her
when
try.
you're trying to like think,
Mhm. Critical thinking that's a perfect way to put it, Maven. Yes. Being skeptical means if I tell you something, don't take it as gospel truth. Don't take it as that is absolutely true because so-and-so said it. No. Always question it yourself. Always look for evidence yourself. And this year we focus a lot on how to determine what is good evidence so that you can make decisions. This class in particular, my earth science class, focuses a lot on who you're getting your information from and what does that information actually mean when you get all the data and you analyze it. What does it mean? All right, so also ask questions. Always ask questions. Don't do the thing where you just assume everything you're hearing is correct. Ask questions about it. Yes?
what does that do?
At the end of class, I'll tell you. Good point. And believe in the process. Okay, this is important. The process of science, when done correctly, and be trusted. Believe in the process.
I'm not going to believe
But that's
in it.
different than believing in the discovery that people come up to, the point they make, the conclusion. The conclusion is not always the same. You can take the same information and come up with different conclusions about what it means. But the process can be trusted if you're doing it right. It's when people do the process wrong that you get really bad science, right? All right, so let's talk about using a scientific approach. How do we approach things scientifically? So what is an organized plan for gathering, organizing, and communicating information? This is a vocabulary word for y'all. Do you know what this one is? This is scientific method, okay? This is where good science happens. And the goal of any scientific method is to solve a problem or better understand an observed event, something you've seen happen, right? So what is information you obtain through your senses? Observation, right? Okay, you think about observing, usually you think about visual. You think about what you see with your eyes. Like if there was a car,
sitting down.
that's when you can stretch. If there was a car accident and somebody might say, what did you observe? It's not just what you saw. It's not just one car hit another. It's, I heard the tires squealing. I smelled gasoline after they hit each other and it started pouring all over. Those are all observations. It's everything that you bring in through your senses. And this is a good vocabulary word that we will be using a lot. What is a proposed answer to a question? Do you know? They know? This is a hypothesis. This is a proposed answer to a question. I hypothesize that Maven is happy to be here today, and I hypothesize that because she's smiling a lot. Now, that's a proposed answer to a question. If somebody said, is Maven happy today? I would say, I think so. I hypothesize that she was. It's like saying, I think. Okay? All right. Now, scientific method is an ongoing process. It's not necessarily a straight line. It doesn't go one way. It doesn't go from point A to point B. There's a lot of rerouting, changing plans, redoing things, trimming down your process and making it more of what you need it to be to get to the answer that you're looking for. And it may not be an answer, it's just a specific answer, but it's an answer, right? So who came up with the idea of scientific method? Lots of people. Aristotle, this is an old dude, 384 to 322 BC. This guy's been gone a long time, and this is a big thinker. He's a big thinker. We talk a lot, people talk a lot about Aristotle, especially philosophy.
Is that why it says?
I guess so. So Aristotle came up with it. We have this guy. I'm going to do his, is it Ibn? The first name I think is Ibn, right? Al-Haytham. And this is, he lived in Iraq, Egypt, Arabia, that part of the world.
Because boys sometimes
946, yes, probably would have been by 946. And then you've got Francis Bacon, who's an English dude, right? He talked a lot about scientific method. He brought in the idea of hypothesis. And then also Galileo Galilei. Does anybody know what he's like probably best known for? Do you know?
Space.
He's the one that figured out the sun.
The heliocentric theory. So back in his time, people believed that the sun revolved around the earth. The earth stayed still and the sun moved around the earth. And Galileo Galilei came out and said, no, actually, I think the earth is moving around the sun. And he was the first one to propose that. He actually got a lot of criticism for it because in the time people didn't want to hear it. Question?
Are you a mother?
A mother? Yes, I have 2 adult boys.
Where are they?
One of them is at gymnastics practice and the other is upstairs, but usually he's in Texas. He's just visiting. So variables. We have variables when we do experiments. So we have a variable that is what you change. And we call that variable either an independent variable or a manipulated variable. There are 2 different words for it. And depending on which textbook you're using, it might be called one or the other. But that is what an independent variable is. It is what you change. Then we have something that changes based on whatever you're doing in the experiment. And that is called your dependent or responding variable. And don't worry, we'll go over these many times this year because it comes up in a lot of the labs that we do. And then we have a standard for comparison. This is what we keep the same, and it's a controlled variable. So I mentioned, hold on, I mentioned in, if you watch the How to Science video, does anybody remember what example I used? What example do you remember? So I use an example of I have a headache, right? So I have a headache and I hypothesize that if I put a cold cloth on my head, it'll make my headache go away. So if I do that and then I go to a dark room and I take some Tylenol and I put the cold cloth on my head and my headache goes away, how do I know what made my headache go away? I just did 3 different things, right? I need to keep everything the same and change one thing, right? That's a controlled experiment. Yes, ma'am.
Am I allowed to look around after this?
After we do this, you can look around a little. Yep. So what if I said, I hypothesize that girls are smarter than boys? And then I gave everybody a pop quiz on lesson 1. I was like, here, take a test right now on lesson 1. Here you go. And then you 2 scored higher than them. And I said, yeah, that means girls are smarter than boys. Was that a controlled experiment? Think about it. No, because what if some of you haven't read the assignment yet? What if some of you were having trouble focusing today? Or what if some of you don't test well? Or what if some of you have problems reading the test? Then I couldn't say for sure that means all girls are smarter than all boys because Maven and Yusra outscored Yassine and Orion, right? That's silly. That is ridiculous. Ridiculous. There you go. So, drawing conclusions. If your data doesn't support your hypothesis, you can revise your hypothesis and rewrite it, or you can try a new experiment, change it a little bit, see if you can get the results you want. If you're trying to get a certain result, you can change the experiment multiple times. What you can't do is say that, well, I think it would have worked. No, you have to know what works and what doesn't work. All right, so developing a theory. All right, theories versus laws. This is a big one. Okay, yeah, there you go. All right, so a rule or principle that always works the same way under the same conditions is a law. And Sorry, he's grabbing something. He's going right underneath you there, Maven. Sorry. This is Jason. He's the man upstairs. He works upstairs. A well-substantiated, that's my husband. I'm not that old. Hush you. So a well-substantiated explanation of some aspect of the natural world that's not yet verified is a theory. So the way we define these for the purpose of this class is really easy. A scientific law tells what happened, a fact. A scientific theory explains why. It's why something happens, an explanation. Some things are both theories and laws, and gravity is a good example. If I drop the penny, what will happen? What will happen? What will happen? It's going to fall, right? Is that a fact? If I drop it, is it going to fall? Yes, that's a fact. Why? Gravity, okay. Gravity is also the law of gravity. If I drop it, it will fall, right? But it's also a theory in this case. Gravity is one of those ones that's both. And the reason it's a theory is because the theory is that this object has less mass than the Earth. And because the Earth has more mass, it is going to pull the object of less mass to it. Mass is just how much matter there is. If I what?
So if you dropped an earth off
If I dropped an earth onto an earth, okay. So yeah, that's kind of when we get into physical science and we talk about Newton's laws. That's an equal and opposite reaction, right? So if you smashed one earth into another earth, they would both go kaboom. Yeah, absolutely. If you smash the moon into the earth would get knocked off kilter. It would be serious damage, but the earth has more mass than the moon. And there's a whole Newton's law about force equals mass times acceleration. It's a whole thing. All right, so let's keep going. Scientific models. A model is a representation of an object or an event, and it makes it easier to understand, like a globe or a map, right? A graph is, pick a spot. There you go. That's good, because we don't want to distract people too much by moving around. People try to focus. So a graph is a diagram that shows a relation between variable qualities. You'll be doing graphs in lab. They usually have an X and Y axis. A graph would be like, where's the graph one here? This one right here is a great example of a graph. There is an X-axis and a Y-axis, and you can chart things on graph paper and see the line move, right? A chart is a diagram of information in the form of a table, a graph, or a diagram. So a graph can be a chart, but a chart can't necessarily be a graph. Does that make sense? A graph is a type of chart, but not all charts are graphs. All right, so how do we measure? This is an important one. Units. So when you are in your kitchen, no, it's fine. They're fine. They can wait on me. They know what they're doing. No worries. I don't know. I'll look in a minute when I'm done with this. Whoever's over there can wait. It's fine. No worries. We got just a few minutes left and we want to get through our lesson. So in your kitchen, you probably use a measuring cup, right? Quarter cup, half a cup. No? You use tablespoons.
I never use.
You know, you're not in your kitchen, huh? Okay. Well, you should try it. But in science, we don't use that system. So in science, we don't say feet, miles, inches, tablespoons, cups. We use the metric system, which pretty much the rest of the world uses. The rest of the world, right? There's good logic for what we call, don't stop, for what we call the standard or the imperial system, which is cups, feet, miles, that kind of thing, tablespoons. But metric system is really, really good because everything is in units of 10. So for example, we call it SI units, and because it comes from this French word up here, Système International d'Unité. So that's what it is. So for length, we use meters as our base. For mass, we use grams. For weight, we also use grams. What's the difference between weight and mass? Does anybody know?
Weight is the effect of gravity on.
Yes, weight is the perfect answer. Weight is,
it?
yeah, weight is the effect of gravity on mass. So if I go to space, my weight will change. I will weigh less. Woo, let's go to space.
You also weight as less as a feather.
I will weigh less because I'm farther from Earth, and Earth is what's pulling me.
As much as a feather.
I'll weigh more than a feather. But my mass will not change. The amount of Miss Danny will not change. The amount of Miss Danny stays the same, right? But I will weigh less because the effect of gravity will be different. So area is meters squared. Area is like if I wanted to replace the tile in a bathroom, how many tile do I need, right? And volume is is meters cubed. So that would be like if I wanted to fill my entire bathroom with foam, the whole bathroom, floor to ceiling, wall to wall, that would be volume, right? Then we have density, how much mass.
Volume is
Mhm.
that how loud.
That's a different kind of volume. So density, how much mass is contained in a space. If I had a ball that was a marble and it was glass, and then I had the exact same shaped sphere and it was cork, which one's going to be more dense, do you think? Cork or glass?
glass.
Glass. If I put them in water, that cork's going to float because there's less mass contained in that space. It's more spread out, right? But glass is very dense.
This traps air.
Mm-hmm. All right, so we also have time. Time we use seconds. All right, and then temperature, we use Celsius most of the time, not Fahrenheit, which is what you're used to. When we say it's 100 degrees outside, we're talking about Fahrenheit, right? We use Celsius in science, which takes a little while to get used to. And then you saw this in your previous lesson, but right here is how we determine our prefixes. So a tenth of something is a decimeter, for example, but 10 meters is a decameter. And then you have centimeters, hectometers, for example, millimeters, and kilometers. We'll use all of those and they'll become familiar to you as we use them. Hold on a minute. I want to whip on through. We have a few more things and we're watching time. We've had lots of questions. All right, when you do scientific notation, you guys won't be doing this too much on your own, but you might do it in lab, especially when we get to, like we do chemistry in 2 more years. If you're still around, you'll be doing this a lot. The reason we do this is because it takes a huge number and makes it workable. So we take a giant number like this number here at the top. This is a huge number. Well, that's a very small number. It's a very small, but look, huge number of digits. And this is a very big number. So for scientific notation, we will make it times 10 and then an exponent. And I'll just show you. And the reason we do it in threes is because when you separate a number, like when you write 1,000, it's supposed to be 1, 0, 0, 0. There's your 3. If you said it was 42,000, it would be 42, 42, 0, 0, 0. That's where the 3's come in. I'll get your question in a minute. I'm trying to get us to the end here. So what's a system? You've got systems in science. These are just examples of systems. Don't worry about them too much. It's a group of interacting or interrelated elements. We'll talk a lot about systems this year. Types of systems. We have thermodynamics. We'll talk a little bit about that this year too, but this is the fun thing about thermodynamics. First, we discovered the first, second, and third law, and then we came up with the 4th law. And instead of calling it the 4th law, for some reason, somebody called it the 0th law. It's the only example I know of that, and it's real weird. All right. I do. Can you sit for just a minute? We're almost done. We're trying to get done. We've only got a few minutes left. An open system can change energy and matter within its surroundings. A closed system cannot. An isolated system. So here's the difference. I'll show you real quick. An open system would be like water on the stove. It's exchanging energy with the environment, right? A closed system would be a balloon, and it doesn't trade anything with the outside of the balloon. But if it was hot, it doesn't change matter. This changes matter and energy. The water will evaporate. You will lose water. That's matter. And heat is there, that's energy. In this case, you have a balloon, it's not going to let the air out, but if it was filled with hot air, eventually it would cool down, right? So it's exchanging energy, but not mass. Yeah, you are actually taking some of it. And an isolated system would be like, we don't really have them. The closest example we have is like a vacuum sealed thermos. An isolated system would be a system where there's no exchange of energy or mass, and it's kind of an idealized system because it's really hard to replicate. Earth has a geosphere. It's your crust, mantle, inner core, outer core. Earth has an atmosphere. It's the gases that surround it. And we're going to talk a lot about these. We have hydrosphere. These are all our systems, right? We talked about the water on the Earth. We have a biosphere. It's the living things on the Earth. Now, lab safety, we went over these before. So you should know them because we went over them before.
I forgot.
We'll go over a couple more before we start. All right, real quick here. If you have your homework, I will put this up and you can look in your binder to check your answers. I'll give you just a second to peek and check your answers. You can also always come back and look at this. It will be filed where you can access this slideshow at any point. And then here are the rest of these. All right, Yusra, you asked what the table is, right? Yeah, you pointed to that table and said, what's this about, right? It's actually, this piece is from a baby grand piano. And this is just a piece of glass on top. That's all it is. Excellent. All right, so now here's what Yep. So now here's what I need you guys to do. We're going to get ready for lab. So what I need you to do is find your lab